the carbohydrate chapter. So this is the first of the biomolecules, and the first important one. We'll cover carbohydrates, and then we'll cover the proteins, and DNA. We'll see how much we can do on the DNA. So the carbohydrates, as the name suggests, a hydrate means water. So as if for every carbon, we have one water molecule. So the general formula is CnH2n. Okay. So they were once thought to be hydrates of carbon, and that's how they got the name. And the carbohydrate, they're synthesized in nature by photosynthesis. Okay. So during photosynthesis, carbon dioxide combines with water to form the glucose molecule. Respiration is just the opposite of the process. It's a breakdown of glucose to give carbon dioxide and water and give back energy. And that's how we get our energy by utilizing carbohydrates. Okay. Now, the carbohydrates, they are giant molecules, but each of these giant molecules are made from smaller units, and they're called monosaccharides. Mono means one, so saccharides is the sugar unit. So monosaccharides are single unit. Okay, so they are the basic unit that forms the full carbohydrate when they join together, like glucose. Okay, and when two molecules join, we call them disaccharides. Now, in this course, we'll be covering three basic disaccharides: sucrose, and we'll be covering maltose, and as for the polysaccharides, means many, we'll be covering glycogen, starch, and cellulose. Okay, just the basic structure. So you can see the monosaccharides, they join together, okay, with elimination of one molecule of water. Okay, and you get, and the linkage, if you look at the linkages, these are ethyl linkages. So carbohydrates have ethyl linkage. Okay, so they're linked to one another by ethyl linkage. Now, in our body, we have enzymes doing the job. Okay, in the lab, we have to do elimination reactions to get this ethyl linkages. But in our body, at our body temperature, which is the normal temperature, 37 degrees centigrade, there are enzymes, active enzymes that can, eliminate these water molecules and put these ethyl linkages. Okay, and also there are enzymes that can hydrolyze them. The opposite reactions, like sucrase enzyme, that flips the sucrose molecule, okay, into glucose and fructose. So monosaccharides, you can have monosaccharides that have 3 to 8 carbon atom chains. Okay, and one of the carbon in this monosaccharides, the carbonyl group. So when I say carbonyl, it can be aldehyde or a ketone. Okay, like erythrose and erythrulose. And you can see that there's an aldehyde and there's a ketone. So in general, we have two kinds of carbohydrates. We have the carbohydrates that contains aldehyde group, we say aldolases, okay, Aldos, or if it contains the ketone, we say ketose. And we saw the reactions of aldehyde in the previous chapter. So aldehydes can reduce, they are reducing power because of the aldehyde group. So that's why they can reduce the tolerance reagent to give the silver mirror. Okay, so we call them reducing sugar. Okay, if they contain a aldehyde group, or if they contain a ketone group, we say a non-reducing sugar. So there are two classes of sugars. So the kind of question that you'll get is something like this. Okay, that I'll give a structure, and I'll ask you tell me whether this is aldose or a ketose. So look for the functional group, aldehyde or the ketone. And depending on the number of carbon atoms, You can have a triose, tetrose, pentose, hexose, and so on. So, um, so prefixes of aldose and ketoses are attached to this depending on the nature of the carbonyl group. So you can say aldohexose or a ketohexose, which tells you that this is a hexose, that means 6 carbon sugar and containing aldehyde, or a 6 carbon sugar containing a ketone. Okay, so you can see this example here. So you can have a tetrose. Okay, that means aldotetrose, aldoketose. Now you do not need to memorize these structures. So I will not ask you the structure because there are many, they are complicated. Okay, so we'll omit that part. It's not covered in this course. But the general idea that whether this is aldose or ketose will be there. So classify each of the following monosaccharides as aldopentose, ketopentose, aldohexose, ketohexose. Okay, this kind of simple questions. So this is a ketone, this is a ketose. How many carbon? 1, 2, 3, 4, 5. So this is a keto. So this is basically a pentose. Okay, ketopentose. And next one is the aldohexose, because there's aldehyde and a hexose molecule, glucose. So aldohexose. For this one, it is 1, 2, 3, 4. So this is basically a tetrose, okay, but of the aldehyde. So aldotetrose, okay. And then you can work on this too, okay. So this is the structure of glucose, okay. And you can see this OH left and right. All this has a meaning. So if it is now it is to the right, if it is to the left, it will mean a different compound. So you have to make sure that you know how these OHs are to the left or to the right in each of the carbon atoms. So that's only for the glucose. Okay, now one important concept that we'll be covering in this chapter is chirality, chiral molecules. Now we saw structural isomers. Like we have this ethanol and dimethyl ether. The position of the oxygen is changed. So they are two different, completely different compounds with two different functional groups. And these are called structural isomers. Okay. Now another group of isomers, these are called stereoisomers. They have identical molecular formula, but not structural isomers. In stereoisomers, the atoms are bonded in the same sequence, but differ in the way they arrange in space. That means in 3D, they're different. So if you look at your left hand and right hand, okay, they look almost the same, but you cannot superimpose them. So they are two different, completely different things. So if the same molecule, you should be able to superimpose. If they don't superimpose, they're two different molecules. Okay. Now, the left hand is related to the right hand by one being the mirror image of another. So if you put a mirror, what you see in the mirror is the other hand. Okay, exactly the way the other hand would be. And if you put them together, okay, you can see that they are actually different molecules, mirror image of one another. But if you want to superimpose, they don't. So these are called chiral molecules, okay, or stereoisomers. Stereo means in 3D. And in nature, this is a very important thing. To nature, these are two different compounds. Okay, so mirror image of the same molecule is not the same to it. And all these drugs, medicines, and even the things that we utilize, like the carbohydrates, D and L. You have the D glucose, you have the L glucose. Okay, mirror images of one another. And nature can utilize D form and not the N form. Okay, if you look at the amino acids, so the L amino acids and D amino acids, and nature can utilize the L amino acids and not the D amino acids. So for nature, or the working of nature, natural things, the stereoisomers are very, very important. Okay. So if you look at these globs here, they are chiral. So and one of the things that you will notice that if there's a plane of symmetry, that if I imagine a plane going through this molecule, if there is no plane of symmetry, that means the two halves are not equal, then they are chiral. If you look at this baseball bat, it is symmetric. So this, that means it is achiral. Achiral means not chiral. A means negative. Okay, achiral is negative. So this glass has a symmetry. So this cannot be chiral. But if you look at the shoe is not symmetric, and that's why you cannot put the shoe of your right foot into left. They will not fit. Okay, so this is chirality. Now, the chiral molecules are also called optically active. Why? Because they can turn the plane polarized light. If you look at the molecules here, like if the a carbon is chiral if one carbon is bonded to four different atoms. There's one easy way of figuring out. And you can see there's no plane of symmetry. If you look at the two halves of the molecule, so if you look at the two halves here, they are not same. You have bromine on one side and chlorine on another side. And if you take the mirror image, you cannot superimpose. So if you take these two molecules and try to superimpose them, you can see this bromine and chlorine and this bromine and chlorine, they are not superimposing. Even though the other two did superimpose, the two groups didn't superimpose. Sorry. So they are different molecules. But if you have two bromines, that means if the four groups attached are different, then you can superimpose. So here you are turning the molecule so that you can superimpose. And if you rotate, so rotate it like a top, holding the hydrogen. If you rotate it, okay, they are not, they are equal. So this molecule here, this molecule here and this molecule here are same. Okay, you can superimpose them. So they are, if two groups are equal, so, or in other words, if all the four groups are not equal, not different, then that is not a chiral molecule. So they are same. Okay, now you get simple question like this. So if I give you a structure, and ask you these questions, okay? For each of the following, indicate whether the carbon in red is chiral or achiral. Okay, what do you think about A? So first check that whether four groups are different or not. If they're not different, if any two are same, then it is not a chiral molecule. So you can see there are two chlorines.
Yes.
So this is achiral. This cannot be chiral.
Oh, okay. That's fine.
And if you look at, yeah, very simple. If you look at B, the four groups attached to the carbon atom are different. So this is a chiral molecule.
Okay.
Now, if you look at C, you know, uh, the carbon is attached to three groups only, not four. So this is not a chiral molecule. How about this one? Study check. Circle the two chiral carbons. So first, are there four groups and are they attached to four different ones? So so which carbon do you think are chiral? Is this one chiral?
Yes.
No, because there are two hydrogens.
OH.
So there are two hydrogens.
Hydrogen.
So not all four groups are not different. So this is not a chiral. If you look at this one, is this chiral? You have this group, you have this group, and you have this group, and you
Mm-hmm.
have a hydrogen. So all four are different. So this is chiral.
Mm-hmm.
And if you look at this one, is this chiral? Same idea. You have four different groups. So this is chiral.
Mm-hmm.
But not this carbon atom. This one is not chiral.
The
So just
Aldo.
Just look at it closely. If there are four different groups attached to the carbon atom, four. If there are three, then it is not a chiral. It has to be four. Now, drawing Fischer projections. So carbohydrates, as you can see, are pretty complicated molecule, right? So the chiral atoms and there are all these groups attached to it. And this way of drawing, it's called a Fischer projection. Now, in the Fischer projection, this is how you do the Fischer projection. So you hold the molecule. Now, carbon has four bonds. So if you look at the carbon is actually tetrahedral molecule. So this is a wedge dash notation. So this is how the carbon molecule, like a tetrahedral. Each angle is 109.5. So if you hold the molecule, something like this, okay. So as if uh, you know you are holding this molecule, two bonds are coming towards you. Okay, we draw a solid wedge, and two bonds are going away from you. Okay, at the back, it's like a fan. Okay. Now, if you join this line, and if you join this is called Fischer projection. So you are basically joining the horizontal lines and the vertical lines, and the center represents a chiral carbon. This is a simple way of representing a chiral carbon, and this is called the Fischer projection. Now, if you look at the Fischer projection, the OH is to the left. We call it L, and they're mirror images. Okay, otherwise D. So L and D are related to each other by being uh, mirror image of one another. And when they're mirror image of one another, we call them enantiomers. Emil Fischer devised a simplified system of drawing stereoisomers. Okay, and these are vertical lines represent the bonds that project backward, and the horizontal lines project forward. The highly oxidized carbon is placed at the top. So that is how we hold the molecule. So the aldehyde group and the ketone group are at the top. And the intersection of the vertical lines and the horizontal lines is what is the carbon atom, and usually the chiral carbon. And a designation D or L stereoisomer is determined by the position of the OH attached to the chiral carbon. So if you look at the OH attached to the chiral carbon for this case, okay, is D to the left and L to the right, and they are mirror image of one another. Now, if there are two or more carbon atoms, what do? You do the same to draw the structure, but to give it the D or L, you look at the chiral carbon, which is furthest from the carbon. That means here this is the furthest. So you're looking at the carbon, which is furthest from the aldehyde. That means this one. And if the OH is to the left, we say L. If the OH is to the right, we say D. This is L erythros, D erythros. If you look at this one, identify each of the following structure as chiral or achiral. Okay, so if you look at this structure, four different groups. So A is going to be um, A is going to be chiral. If you look at B, you have a CS3, you have a H, you have a C2H5, and bromine. All four are different. This is chiral. If you look at C, this carbon, so we are looking at this carbon. Okay, here we are looking at this carbon. Here we are looking at this carbon. Now this is not chiral. No, no, this is not chiral because you have two same group. This is not a chiral molecule, the first one. But the second one is chiral. The third one is chiral. And if you look at the fourth one, two same group, not chiral. Okay. Okay, let's try to figure out. So what do you think? Now, as I said, the mirror images are called enantiomers. Okay. So the stereoisomers cannot be superimposed and they are called enantiomers. So the mirror images are called enantiomers. Okay. PR of enantiomers. So if you look at these two, are they enantiomers? Are they mirror image? First, are they chiral? Second, are they mirror images? If they are superimposable, then they are not chiral, the same molecule. Superimpose, that means if you look at facial recognition, if you can superimpose a face on another, they are same thing. Okay, so same for molecules here. So if you can superimpose, then they are not chiral. So here, now you have 4 different groups, but no, you have, these two are same. So they are identical. We will say identical. So even though they mirror images, you can superimpose them. So if you turn the molecule, you will see that the chlorine will exactly match with the chlorine. Okay. For second one, you have 4 different groups. Okay, and so are they mirror image of one another? So if I hold a mirror, they are mirror images. If they are enantiomers. So are there 4 different groups in C? Yes. And if I hold a mirror, are these 2 mirror images? Yes. So you can see the bromine nearer to bromine, chlorine further, chlorine here. Okay, they are mirror images. And so they are enantiomers. How about this one? There are 4 different groups, and if I put a mirror here, they are basically reflection of one another. So they are enantiomers. So indicate whether each pair are enantiomers or identical. Same question, okay, a similar question. So 4 different groups, yes. And are they mirror images? Yes. So these are enantiomers. Now these are mirror images, but these 4 groups are not different, not same. They're supposed to be different, but they're not. They have 2 hydrogens. Okay, so these are identical. Similarly, if you look at the next one, so you can see there's a mirror image. 4 groups are different. These are enantiomers. And for the next one, this is a aminoaldehyde. Okay, so 4 different groups, mirror image, yes, and these are enantiomers. So the enantiomers in nature, L-carbon, carbon extracted from spearmint and carbon extracted from caraway plant, they taste different. L-dopa, D-dopa, these are drugs. Okay, this is the L-dopa and this is the D-dopa. Then you have adrenaline and nicotine. They have similar chirality. And that's why nicotine, kind of acts as a stimulant, just like adrenaline does, epinephrine. So now in nature, these are different molecules. So if you look at this molecule here, okay, you'll see that this is a mirror image. So apparently they look the same, like our left hand and right hand. But if there's an enzyme surface where this one exactly fits into these groups, but if you look at the other one, it is not fitting into this group because the enzyme surface itself is chiral, and they can distinguish. Like if somebody presents the hand for shaking, you can shake the right hand to the right hand. Okay, you cannot shake the right hand to the left. Okay, they do not fit. It's same like handshake. Okay, the enzyme is projecting the hand to grab something, and it has to exactly match. And the mirror image doesn't match. Okay, so the other enantiomers are not recognizable by the enzyme because of this. Now, if you look at other molecules like ibuprofen, we use it, for fever and painkiller. But ibuprofen, only one of the isomer is active, the other one is not. So the companies, if they really want to treat you, they should give you one single enantiomer, which is hard to purify. Okay, so they often give you a mixture. So that's why that mixture, the other part, basically does nothing. It increases the acidity and does all kind of trouble. But they can give you a cheaper drug. So that's why the brands that you see from different companies may not work the same way, or may not have the same side effect because of the other enantiomer present, okay, which is not the active ingredient. But again, it's hard to purify single enantiomers. So enantiomers are very much related to their physical and chemical properties. Okay, so they have the same melting point, same boiling point, same kind of interactions. That's why it's very hard to purify one enantiomer from another. These are monosaccharides, the large molecules. So the rule is you hold the molecule like this with the oxidizing group pointing up. That means the aldehyde pointing up. And to give the L and D, you look at the farthest, the chiral carbon that is farthest. So in this case, this is carbon number 4, okay, or carbon number 5 for the hexose. So the OH to the left is L, OH to the right is D. Now, you don't need to memorize the structures, but I will give you a structure. And I'll ask you a simple question like, tell me whether it's L or D isomer. So just look at the chiral carbon that is farthest from the aldehyde. Okay, if it is to the left, is L. If it is to the right, is D. So this 3 is what we have for this course: monosaccharides, glucose, galactose, fructose, and we'll see how glucose and glucose gives a disaccharides, and glucose and galactose, or glucose and fructose gives disaccharides. So we have 3 disaccharides for this course. So glucose is maltose, glucose galactose, and then glucose fructose would be the our common sugar. Okay. Now this is a structure of glucose that is unstable. So what happens, because the aldehyde group being reactive, and this cannot stay in nature like that. So what it does to give stability, this OH combines with the CHO, basically forms a ring. Okay. So what you have is this OH basically combines. We forming a ring, not this OH, this number 1, 2, 3, 4, 5. Usually this chiral carbon 6-member ring. Okay, so that means, and this is called the howarth structure. Okay, this is what you see in many textbooks. Like if you look at a microbiologist textbook with the our cell wall, bacterial cell wall, these are made of carbohydrates. Okay, and if you look at the structure of the carbohydrate, you will see this ring structure. Okay, and that's because that is how glucose exists. Now, in order to do the howarth structure, you let the molecule fall on the side. So you let the molecule fall on the sides on the right, and then basically fold it and join it. Okay. Now, what is important in the howarth structure is if you look at carbon number 1, this is not chiral carbon, but once it forms the ring, it becomes chiral. Okay. And if it is chiral, then you can have OH pointing up, OH pointing down. Okay, 2 isomers, 2 additional isomers, and they're called the alpha and the beta. So OH pointing up is the alpha, OH pointing down is called the beta. Now, and you'll get a question from this, identifying the alpha and beta. Like I'll give you a structure like this, and I'll ask you that tell me whether this is alpha or beta. So how do you identify the chiral carbon? You look at the oxygen right beside the oxygen, because that is the one forming the bond, right? So right beside the oxygen, you have this chiral carbon. Okay, and if you look at the chiral carbon, the OH is pointing down, that's alpha. The pointing up, that's a beta. So mutation of alpha and beta glucose. Now, what I didn't tell you is these are also called optical isomers. That means if you pass a pen polarized light, so we use a polarizing glass, right? So we often use that polarizer. What a polarizer does, it allows only light in one plane, vibrating in one plane to pass through, but it cuts away light from other plane. So if you take a plane polarized light that is vibrating in one direction, and if you pass it through these compounds, it rotates the plane of polarization and it vibrates at an angle. Okay, so we say mutual rotation. So this rotating of the light we call mutual rotation. Now, and we can calculate the angles by which they are you know rotating. So the alpha and beta, if say the alpha rotates by 20 degree to the left, the beta will rotate 20 degree to the right. So D and L, the two enantiomers, they rotate the light exactly by the same amount, but in the opposite direction. So if the two isomers present in equal amount, then you will not see any rotation. They cancel each other. And this is called the racemic mixture. Okay. But like if you take a pure D glucose, okay, and put it in water, what happens is ring opens and closes. This ring, because this bond is open and closed, and if you keep it for a long time, you'll gradually see that both the isomers are being produced, okay, like the alpha and the beta, like an equilibrium is established. And in that, we have 64% glucose and 36% of the alpha D, okay, beta D and the alpha D, 36, 64. You started with 100%, and now it becomes 36 and 64. So naturally, the plane of polarization of the light will change, and this is called mutual rotation. So if you look at galactose, Howard structure of galactose is basically similar to glucose, only the 4 position has changed. But what is important to note is the alpha and beta. Okay, so alpha is pointing down, beta is pointing up. So this is the alpha and beta. So this is fructose molecule. So fructose, as you know, is a ketose, is a keto group. So the bonding, basically happens with the carbon number 2 when it cyclides. So you are left with a CH2. You have to practice this drawing, okay? So you can see the CH2 is the one CH2H is pointing up here. And the chiral carbon is the number 2. That means this is the chiral carbon, number 2. And the OH can be pointing down, OH can be pointing up. Okay, so you can have 2 forms of fructose, alpha fructose or the beta fructose. Okay. So numbering carbon atomic Howard structure follows the same pattern as the pentagon. So always start with the chiral, the first. So you are keeping the numbering the same. So 1 is still the CH2H. Now, this is a flat structure. All the structures are flat structure, but this is not how carbon is actually tetrahedral, right? So, so if you draw it in the real sense, this is how a glucose molecule looks like. Okay, if you try to do it in 3D, okay, and so these are equatorial and axial groups. So in 3D, we basically, uh, this is there's a hydrogen here, and we call it axial position, and this is equatorial. Similarly, we have a hydrogen up here, and this is axial. Okay. Axial means pointing up, equatorial means pointing down. So as if along the equator, okay. Axial is pointing up always. So these are axial. So this is the actual 3D structure of glucose, and it can flip. It can flip means so glucose is a very dynamic molecule, and so this is one chair form, and it can flip. So you can flip this up and flip this down like a hinge, okay, and they are at equilibrium. These 2 chair forms are at equilibrium. Okay, so this is the actual structure of glucose. So glucose is simple, but not that simple molecule. And that's why in nature utilizes glucose because it can make so much variations with that. Okay. And with the same hexose, you can get like 16 different compounds with the same hexose formula. Galactose, mannose, tagatose, you have the glucose, so many, and then you can get the fructose also. So another 16 there. So mind-boggling. Okay. Identify each as alpha or beta. Okay, so this is the chiral carbon here. So let me clean it up. So if you look at this alpha, this anomeric, so this is called, by the way, this new carbon atom that is formed, this is called anomeric carbon. Okay, okay, the new carbon that is formed upon cyclism. Okay. So this carbon is called the anomeric carbon, or this carbon here is the anomeric carbon that is formed, new chiral carbon formed by cyclism. Okay, so we are referring to the anomeric carbon for the alpha and beta isomer. So OH pointing down, so that means is axial. So basically, uh, this is the beta. Okay. No, OH pointing down is the alpha, and up is the beta. So this is the is basically the alpha isomer. Okay, and this here is the alpha isomer. This is the next one, and again this is the anomeric carbon, OH pointing up. So this will be the beta. You have to memorize that up and down. Okay, this is the beta, and this will be this is the beta, and this is the alpha. So this is the only thing that you need to do. Point out alpha or beta. Okay. Now, chemical properties of the monosaccharide. That means we are looking at one unit, monosaccharides. So the monosaccharides, depending on whether it's an aldehyde or ketone, you can oxidize the aldehyde, and they are called reducing sugars. Okay, reducing sugars. So if you use the tolerance reagent, ammonical silver nitrate, you get a silver mirror, and the corresponding aldehyde, they get oxidized to an acid group. So same for the glucose. So if you do that on a glucose, then it becomes gluconic acid. You can oxidize the Benedict's reagent. For the Benedict's, remember, it needs a adjacent OH. Okay, and that we always find in carbohydrates. So Benedict's reagent is a good test. Okay, and so if you add the copper sulfate reagent, it gives a big red precipitate of copper oxide, and the corresponding, the sugar, it gets oxidized. That means the aldehyde becomes acid group, and that's a gluconic acid. And for naming this acid, the corresponding carboxylic acids are named by replacing the O's with an oic acid, so gluconic acid, oic acid. So fructose, a ketohexose, is also reducing, and that is not supposed to be reducing because it is ketone, but it becomes reducing if you keep it for a long time in the reagent. Okay. But if you do a 1 minute test, it will not respond. But if you keep it for 10-15 minutes or boil it, so there's a rearrangement that happens. Fructose can rearrange to glucose very slowly, but it does. And it is this glucose part that reacts with the medicine. So oftentimes we see a positive test, but very slowly, but positive with fructose because of the rearrangement. Now we can reduce the, just like an aldehyde, we can reduce the aldehyde group. And if you reduce the glucose, you get sorbitol. Okay, that means the CHO becomes CH2OH. Upon reduction, glucose gives sorbitol. So now we'll come to the disaccharides. So disaccharides, they're formed from two monosaccharides linked together by ethyl linkage. So if you dehydrate, yeah. So in our body, it is done by specialized enzymes. Okay. So glucose and glucose, when they join, we get maltose. Glucose and galactose, when they join, we get lactose. And glucose and fructose give sucrose. These are three molecules we'll be studying. Now, the problem is there's so many OH. So who is undergoing the dehydration and how we are getting the linkage? So when you're getting the disaccharides, it is very important to tell what is the linkage. So so if you look at the maltose, okay, this is a 1,4 linkage. Okay, 1,4. Now, the glycosidic bond is between the OH, okay, OH group of the carbon, and carbon 1 and carbon 4. Now, if you look at the product, the second carbohydrate. If you look at the second, that is the carbon on the right. And if you look at the anomeric carbon, it's still open. That's still reducing. That means it can open and close. It can form the aldehyde. So it will give you the aldehyde test. And on that, if you look at the product, if the OH is pointing down, we call it alpha. So the product, so this is 1,4, maltose. What kind of maltose? This is alpha maltose. Okay. So you see at the bottom, alpha maltose. But if the OH is pointing up, we will call it a beta maltose. So two things that we need to point out when you form a disaccharide: what kind of linkage and what kind of product. Okay. So this is a alpha 1,4 linkage. Alpha, because these two bonds are alpha. So if you look at the first carbohydrate, the OH is pointing down. So this is alpha 1,4 linkage, and the product is alpha. Now you can have an alpha 1,4 linkage, but a beta maltose. If the OH on the right is on the basically on the up, then this becomes a beta maltose. So alpha 1,4 linkage, but a beta maltose. So you have to look at the bond and say which carbons are joining, and that is alpha or beta. And you have to look at the product finally and say whether the product is alpha or beta. So 4 things that you need to check. Okay, so if you look at lactose, okay, so in the case of lactose, it's a glucose and galactose joining. If you look at the first part, the one that is presenting the anomeric carbon, so that's the first carbon, okay, the first carbohydrate, the one which is giving the anomeric carbon. So here the OH is pointing up, that means it's a beta. So it's a beta 1,4 linkage. So the linkage is beta 1,4. Okay. But if you look at the product has a OH pointing down, that means it's alpha. So it's alpha lactose, but the bond is beta 1,4. And you can imagine nature utilizes all those, giving you a different compound. It will not be lactose, it will be something else, but the same disaccharide. So you have to be very specific. Nature is very specific about what it is doing. And the small difference can be detrimental to our health. Okay. So if you look at sucrose, now sucrose is a disaccharide between glucose and fructose. Okay. And the bond that you can see is alpha, is basically pointing down. That means it's alpha. And 1, 2. And when you do 1, 2, both are anomeric. Both are anomeric. Okay. So this carbon is anomeric carbon number 1, and the carbon number 2 is also anomeric carbon. So this the linkage is beta 1, 2 glycoside linkage, because it's alpha beta. So alpha to one and beta to another. So alpha beta. So the first one is pointing down. So that's alpha, and the second one is pointing up. Now, because both are anomeric, so we are concentrating on the anomeric carbon. In the other cases, we didn't have to do both, because this is number 4 is not anomeric. So we just said beta, depending on number 1. But here both are anomeric carbon. So we have to say alpha beta 1 to glycosidic linkage. And the product, because the anomeric carbon is blocked, we don't have to say anything. So just sucrose. So sucrose will not have alpha sucrose or beta sucrose. So this, we have 3 then. So going back again, if you go to maltose, okay, so the carbohydrate 1 is the one that is presenting the anomeric carbon for the bond. So, and then there's the carbohydrate 2. And you have to say what linkage, 1 to 4. But alpha or beta linkage, so you look at the anomeric carbon, the first carbon, and it's pointing down. So the OH pointing down, which is alpha. So alpha 1,4 glycosidic linkage. So the linkage is alpha 1,4. The product OH is pointing down. If you look at the anomeric carbon of the product, so you look at the second carbohydrate, the OH is pointing down. So that means it's alpha. So this is alpha maltose. If you look at the lactose here, given this picture, So this is 1,4 linkage. Okay, but in the bond, the OH is pointing up. That means that's a beta. So beta 1,4 linkage. But if you look at the product, the overall product, and if you look at the second carbohydrate, the OH is pointing down, which is basically a alpha. So this is alpha lactose. Okay. And for sucrose, because you are utilizing anomeric carbon of both the sugars, so you have to say alpha beta 1 2, and the product, doesn't have to say anything because the anomeric carbon is gone. There is no H. So just sucrose. So these are the three disaccharides we need to know, okay, for which we'll get into a question. Now, if you look at the disaccharides, um, or the sugars in general, so monosaccharides, disaccharides, and if you have a way of measuring the sweetness, which they do. So this is the level of sweetness that you have. If you take the standard sugar as 100, galactose is much less sweeter than glucose. Fructose is more sweet. And if you look at all these sweeteners, artificial sweeteners, they're many, many times sweeter than our regular sugar, sucrose. Okay. Now, nature utilizes all these linkages because they're different molecules. Right? It's like, for identification of cell types is one, and for address, like protein sortings. So when the proteins are made, where will it go? So carbohydrates serve as like a address tag, okay, like sorting. So it's a huge field, but this is just one example of use of carbohydrates for cell types. So if you look at the blood cells, okay, you have the blood type A, B, and O, and they're different in the surface tagging of the carbohydrates that you have. If you look at, these rings are basically carbohydrates, not exactly carbohydrates, but derivatives. Like you have the galactose, but you have the N-galactosamine. That means the amine group is there. But anyway, there are 4 different kinds here. And the linkages are different, how they are linked here. So the blood type O is lacking this single carbohydrate. In the blood type A and B, you have this carbohydrate at the end, but they are different. For blood type A, you have the N-acetyl glucosamine. For blood type B, you have this galactose. Okay, so they are different, and they are recognized as 2 different cell types. And that is how we basically test. And the compatibility, I don't know whether it still holds good. So if you have a blood type A, now these surface antigens, they generate antibodies. So the antibodies recognize if you have a blood type A, it produces antibodies against B and AB. So antibodies cross-react. Okay. So basically, it can receive a group, but not a B. Okay. Anything that has a B tag on that will be destroyed, okay, or cross-react. Okay. So this is something just to keep in mind, and the carbohydrates play a role in that cell types. Okay. So you'll get. I'll not ask you what are the monosaccharide units. Okay, so you can omit that question number 8 from here. But I'm going to ask you what type of glycosidic linkages are there. So these are 1,6. So here, when you look at the carbohydrate, we'll see that the branching in the carbohydrates occur 1,6, and the enzyme that works on the 1,4 cannot work on the 1,6. Okay, so nature controls that too. Okay, how it is going to retrieve back the carbohydrates. So, this is a 1,6, and in the anomeric carbon, the OH is pointing down. Okay, so down means it's axial. So basically, it's alpha. Okay, so this is alpha 1,4. Now the solution is given here. Okay, so 1,6, so alpha 1,6. And if you look at the product, okay, the OH is pointing down, so that's the alpha product. So this is alpha millibias. Now you don't need to identify it's millibias, or you don't need to identify any of these units here. I'm not going to ask you those questions, but I'm going to ask you questions regarding uh, regarding the uh, regarding the linkages uh, and the stereochemistry of the product. So again, I'm not going to ask you the first question, what is the linkage, but I'm going to ask you the linkage. So this is a beta 1,4 linkage, and this beta lactose. So if you look at the carbon number 4, OH pointing up, okay, OH pointing up means it's a beta. This is a beta lactose. Now, if you look at this, B is a, now, okay, so one important thing is numbering. Okay, so you have to learn how to number given a structure. So if I number, always start with the anomeric, oxygen and then the carbon here. 1, 2, okay, 3, 4. So I'll give you a glucose unit and ask you to number it. Okay, you will definitely get that question. So please learn how to number. Okay, and here is 1, 2, 3, 4, 5, 6. Now, for this one, again, you go 1, 2, okay, and so on. So I'm not writing the rest. So here you go 1, 2, 3. So this is carbon number 6 here. Okay, so for this one, again, 1, 2, 3, 4. So these are all hexoses, so no problem. So I'm not going to ask you which unit, okay? So don't bother about that one, but I'm going to ask you what kind of linkage and what kind of product. And this is a sucrose. And in the case of sucrose, remember, you have to write alpha beta. Now this is wrong. I have to write alpha beta. Okay, alpha and beta. So alpha beta 1, 2. And the sucrose product, because the anomeric carbon is blocked, we don't write anything. We just write sucrose. Okay. Now polysaccharides. Poly means many. We have only 3 to look at. Yeah. Starch, glycogen, and cellulose. So if you look at starch, okay, so all you need to know in starch, the starch consists of 2 kinds of polysaccharides, amylose and amylopectin. Okay. And it is used for storage. So amylose, which is basically 20% starch, so it can be like 250 to 4,000 alpha D glucose molecules connected. Okay. And important is what you need to know is this alpha 1,4 linkage. And this is important because that is how the enzymes, you need the alpha 1,4 digesting enzyme in order to utilize the starch. Now, this amylose is kind of simple. Amylopectin, on the other hand, is 80% starch and is branched. And this is the interesting part here. So the main chain that you see is 1,4, just like amylose, but the branching is 1,6. And so if a food is rich in amylopectin, the starch doesn't get digested, so it stays longer time. So when you choose your food with starch, you can basically look at that, we say fibers. So what are fibers? They stay longer time. And that's why they remain as fibers, because this 1,6 linkage, it doesn't get digested that easily. Okay, so starch fibers. So something rich in 1,6 will remain in your system for longer time. Okay, so again, the take-home message is, what is starch? So it's a polymer of alpha D glucose, and it can vary. The length can vary like 250 to 4,000. Okay, that many units. It can be very long, and they are linked by alpha 1,4 glycosidic linkage. Okay, and if you look at, because of this particular 1,4 linkage, you will see the starch molecules are like a spring, okay, they form this coil structure, helical structure, and that is again important. Okay, and along with that, if you have amylopectin, you can have branching, and the branch can have coils too. Okay, so it's like a coil structure. Uh, and how close the branching are? So in case of you know starch, it is like 25 after 25 glucose unit, you get the branching, and the branching is alpha 1,6. Okay, now the starch hydrolyze easily in water and acid. So acid, or you can have the hydrolyzing enzyme, and they hydrolyze into smaller saccharides called dextrins, which then hydrolyze to maltose and finally glucose. So there's steps in the hydrolysis. So first chopping, the next chopping, and the next chopping. Okay. So the first chop gives you, with the amylase, you get dextrins, small fragments. Dextrins, uh, you know, they get further hydrolyzed to give the maltose, which is the disaccharides, and the disaccharide get hydrolyzed to give you the glucose. Now, so, and it happens at different parts of the body. So amylase in the saliva. So amylase is helping it to do the pre-digestion, giving you small pieces, but the actual digestion happens in the intestine with the maltase, giving you the glucose. Okay. So glycogen and these enzymes you will see later in the protein chapter, they are active depending on the pH. So some enzymes, so in the saliva, you have the enzymes, amylase and all those. So they are working in neutral pH. But if it goes into the stomach acid, it will not work. Okay, so that's why these compartmentalization and divisions are there. Okay, glycogen is similar to starch. It's called the animal starch. It's more dense. So more dense because it is highly branched. Highly branched, so the branching is happening like 10 to 15 as opposed to 25 for the starch. And they have the same alpha 1,6 like glycosidic branching linkage. Okay, now so you saw starch and glycogen, they're, they're pretty similar. Now compare that with cellulose. We cannot digest cellulose, remember that. And because the cellulose linkage is beta 1,4, so starch is alpha 1,4. Just make it beta, and we cannot digest. We cannot digest paper, right? But cows can, because there are bacteria that produces in the gut that produces that enzyme. Okay, so cellulose, again, the structure of cellulose is different. So if you see the starches, they are coil. So these are coil structures. This coiling, but cellulose is like straight chain, like a fiber. So that's why you get cellulose fiber, and that because of only one change, and that change it is being beta 1,4. There's no branching. So cellulose fibers doesn't have branches. So you get nice cellulose threads. Okay. So see how all these linkages affect, give you totally different something from the same glucose. Okay, glucose polymer. Uh, okay. Now this is the summary of this chapter. This is a compact chapter. Okay, but you know we covered many basic concepts. So we'll keep it to the basic concept. We'll try to remove the structural part. So I'll not ask you the structure of glucose, but I'll ask you to number the glucose molecule, how you put the number. Because when you do the linkages, you need the numbers. Okay? So you'll get one question like that. Uh, so difference between monosaccharide, disaccharides, polysaccharides, what kind of linkage? They're all ether linkages by the dehydration of sugars. So we have three monosaccharides that we learn. Okay, and their Fischer projections, howarth structure. Howarth structure generates another additional chiral carbon. Okay, we have the alpha and beta anomers there. So remember, alpha and beta. So beta is pointing up, alpha is pointing down. And the structures can be mirror image of one another. So you should be able to give the DL notations, alpha, beta, DL. So when you are doing the DL, you are looking at the carbon that is furthest, chiral carbon furthest from the from the aldehyde carbon. Okay, and the OH is pointing right. We say right is dextra, so that's a D, and or we have the label L. Okay. All right. For the disaccharides, we have to only learn three: maltose, lactose, and sucrose. Okay. So maltose and lactose, they have this in the product. You have the anomeric carbon that is open. Okay, so it is they're reducing sugars. But sucrose, you can see the anomeric carbon both the saccharides are blocked. So that means it's non-reducing sugar. Okay. And the polysaccharides, so we have three. We have the glycogen, starch, and cellulose. So starch is made up of amylose, amylopectin. Linkages are important. Okay, and and the branching structure. So it's a alpha 1,4, beta 1,4 linkage, and for the uh, glycogen and starch is basically how compact they are. Okay, so glycogen is more compact and it has branching uh, every 10 to 15 carbohydrates or glucose molecule in the chain, and while for starch it is like 25 to 30. And there are some additional information here where you get all this. So I'm not going to ask you any specific question, but it's a good reading. But this is where the linkages are. So linkages, memorize that. So alpha 1,4 glycosidic linkage for the cellulose is beta. Okay. So that's all for this chapter.